Well, good afternoon, everyone, and thank you so much for joining us today for the What Works Clearinghouse webinar focused on design comparable effect sizes for single case design studies. My name is Emily Tanner Smith. I'm a Thompson professor at the University of Oregon and a training task lead for the What Works Clearinghouse Statistics website and training contract. On behalf of the Institute of Education Sciences and the WWC, I welcome you to today's important webinar. On today's webinar, the presenters will provide a general introduction to single case designs and then discuss the design comparable effect size that the WWC now uses to quantify the effectiveness of interventions from single case design studies. The presenters will then provide a demonstration of a web-based application tool that can be used for calculating the design comparable effect size. Our webinar today will be led by two experts on single case design methodology and the WWC Standards and Procedures, Drs. Mariola Moyart and Dr. Danny Swan. Dr. Moyart is an associate professor of educational psychology and methodology at the State University of New York at Albany. She's a research methodologist with expertise in single case experimental design and analysis, hierarchical linear modeling, and meta-analysis. Our second presenter today, Dr. Danny Swan, is a postdoctoral scholar at the University of Oregon who works on the WWC SWOT contract. He's a quantitative methodologist whose research focuses on the challenges in the analysis and meta-analysis of single case design data. Now, before we begin today, I will note that throughout the webinar, we will be sharing links to resources within the chat box. We will also be monitoring the chat box for any questions from you as our participants. Towards the end of the webinar today, our presenters will respond to questions received from participants. It's important to note that although we may not be able to address all questions during today's webinar, we will be responding to all of those questions received and include those responses in the archived webinar materials that will be posted publicly to the WWC website. So the learning goals for our webinar today include understanding the difference in quantifying intervention effectiveness between versions 4.0 and 4.1 of the WWC standards, quantifying intervention effectiveness in single case design studies using the design comparable effect size, understanding the logic behind the design comparable effect size and its underlying assumptions, understanding the advantages and disadvantages of the design comparable effect size, and then finally, understanding how to use a point and click Shiny application to calculate the design comparable effect size. So with that, I'll turn the webinar over to our first presenter, Mariola, who will provide us with an introduction to single case designs and the design comparable effect size.
Thank you for the introduction, Emily, and good afternoon, everyone. During the first part of today's webinar, I will first introduce single case design types. Second, I will summarize commonly used approaches to quantify intervention effects in single case design research. Next, I will clarify the main differences in examining and quantifying intervention effectiveness between the What Works Clearinghouse version 4.0 versus version 4.1. To end part one, I will introduce the logic behind the design comparable effect size. Let me start with asking the following question. What is a single case design experiment? Well, single case experimental designs are designed experiments in which one unit is observed repeatedly, and this during different levels of at least one independent variable that is actively and systematically manipulated by a researcher. The levels of the independent variable represent conditions, namely baseline or control conditions and intervention conditions. The unit is measured on one or multiple dependent variables of interest during both control and intervention conditions. Therefore, the unit serves as its own control. By systematically measuring the dependent variable of interest before, during, after the research manipulated intervention, it can be evaluated whether there's evidence in support of a causal relation between the intervention and the outcome variable of interest. Single case design data are hierarchically structured by nature, as repeated measures are nested within units. and usually more than one unit is measured repeatedly over time during one single case study. This allows generalizing intervention effectiveness across units. The hierarchical structure is displayed on the right-hand side of the slide, where you can see that the measurements are nested within units and units are nested within a single case study. There's a variety of different single case experimental design types, including the reversal withdrawal designs, multiple baseline designs, and alternating treatment designs. The Wadsworth Clearinghouse developed standards to evaluate the internal validity of these design types. Single case experimental designs meeting these design standards with or without reservations can be used to provide evidence in support of a functional relation between the intervention and the outcome variable of interest. Now I will introduce an example of the reversal withdrawal design and the multiple baseline design and apply the Wadsworth Clearinghouse standards to these examples. I'm limiting the discussion to the reversal withdrawal designs and the multiple baseline design as a design comparable effect size, which will be introduced and demonstrated later, is only developed for these two design types. A first single case experimental design type for which the design comparable effect size can be calculated is the treatment reversal design. This design type can be abbreviated by ABK. In single case experimental designs, the letter A usually refers to the control condition and the letter B to the intervention condition. K indicates the number of pairs embedded in the treatment reversal design. For instance, AB4 would refer to 4 AB pairs. The reversal design is especially useful if the outcome variable is reversible, which means when withdrawing the intervention, the outcome scores are assumed to fall back to baseline levels. The researchers Loshi and Helfin used an AB2 treatment reversal design, which is graphically displayed on this slide. The researchers investigated the effectiveness of a peer tutoring training program labeled as buddy pairs in the graphical display to increase the percentage of appropriate social skills. The outcome is assumed reversible. The participants were children diagnosed with autism spectrum disorder. In order to meet the Wadsworth Clearinghouse standards without reservations, there's a need for at least 3 demonstrations of intervention effectiveness, at least at 3 different points in time. Now in this study, the research team actively manipulated the independent variable and did have 3 opportunities to evaluate intervention effectiveness within each participant included in their single case study. More specifically, the pattern of outcome scores during baseline 1, A1, can be compared with the pattern of outcome scores during the first buddy pairs intervention condition, B1. This is the first opportunity to evaluate intervention effectiveness. Then the pattern of outcome scores during the first intervention condition can be compared with the pattern of outcome scores during the second baseline condition. This is the second occasion to evaluate intervention effectiveness. And then lastly, the pattern of outcome scores during the second baseline condition can be compared with the pattern of outcome scores during the second intervention condition. This is the third time point to investigate intervention effectiveness. In addition, there need to be at least 5 observations within each conditions to meet the Wadsworth Clearinghouse standards without reservations, assuming that all other design requirements are met. Now, the pair 1 conditions do have 5 observations. However, the pair 2 conditions only have 4 observations. Therefore, this would be rated as meeting the Wadsworth Clearinghouse design standards with reservations. The second single case design time for which the design comparable effect size can be calculated is a multiple baseline design across participants, abbreviated by MB. An example of an MB across 3 participants is graphically displayed on this slide. Dr. Sadler and his research team investigated the effectiveness of self-regulated strategy development on the quality of writing for 3 students diagnosed with learning disorders. A unique feature of the MB design is the staggered start of the intervention across the units. In the graphical display of the MB study of Sadler and colleagues, you can see that the intervention started after session 3 for the first participant, after session 4 for the second one, and after session 6 for the last participant. By staggering the start of the intervention, it can be evaluated whether a change in outcome score occurred for the participant given the intervention, whereas the other participant outcome scores remained at baseline levels. This design makes it possible to evaluate intervention effectiveness at 3 different points in time for the 3 different individuals. Now, in order to fully meet the Wadsworth Clearinghouse standards, at least 5 observations are needed per condition. As there are only 3 observations in the control condition of the first participant and 3 in the intervention conditions, this design can at most meet the Wadsworth Clearinghouse standards with reservations. As there are multiple participants or units, cases, individuals involved in one single case experimental design study, intervention effectiveness can be quantified at a case level and across studies at the study level. Several quantifications have been developed for both levels of analysis. The most common types of within case quantifications are non-overlap indices, which all rely on examination of the distributional overlap of the outcome data across conditions. However, these indices have been developed without reference to parametric distributional modeling assumptions and thus lack known sampling variances. Consequently, these effect sizes cannot be synthesized with conventional meta-analytic techniques in which effect sizes are weighted by their sampling variances. Other indices, such as the within-case standardized mean difference and regression-based measures, do have a known sampling distribution, at least under certain modeling assumptions. And therefore, they can be synthesized using conventional meta-analytic techniques. However, all of these effect sizes are standardized using the within-case standard deviation. Therefore, they cannot be combined in a meta-analysis that also includes standardized mean differences estimated from between group designs. So in light of these issues, researchers may be interested in estimating effect sizes from single case design studies that are comparable to those from between group designs. The design comparable effect sizes are exactly developed for that purpose and is standardized using both within and between case standard deviation, and is therefore an across case standardized metric. So we can go one step further and quantify intervention effectiveness across single case design studies. Single case design studies investigating the effectiveness of a common intervention on an outcome measure that is common across studies for a certain population can be meta-analyzed. This across-study synthesis can provide more external valid findings and can identify evidence-based interventions. In the previous Wadsworth Clearinghouse version, version 4.0, single case design studies were synthesized if the 5-3-20 rule was satisfied. This rule indicated that at least 5 single case design studies needed to be identified with or without reservations. The studies needed to be conducted by at least 3 different research teams, and there needed to be a total number of 20 cases across all the identified studies. Once this 5-3-20 rule was satisfied, review teams tallied and computed the number of intervention effects that were positive or negative. If the majority of the studies provided positive intervention effects, then there was evidence in support of intervention effectiveness. This procedure is also called vote counting. Version 4.0 did not provide recommendations regarding synthesizing single case design intervention effects with intervention effects from group design studies. So 3 major changes were made to the Wadsworth Clearinghouse version 4.0 in terms of how to synthesize intervention effectiveness across studies. First, version 4.1 of the Wadsworth Clearinghouse standards is now explicit about which effect size to use to quantify the intervention effect. The Wadsworth Clearinghouse recommends using the design comparable effect size. Second, this design comparable effect size can be synthesized with effect sizes from group comparison designs, such as HSG. Third, instead of vote counting, so calculating the proportion of positive interventions, a fixed effects meta-analysis is recommended. Studies included in the meta-analysis are weighted by the inverse of the sampling variance of the design comparable effect size. Hedges and his colleagues proposed a design comparable effect size for single case design research. This was also called the HSP estimator. They used a hierarchical linear modeling framework to define a D-type effect size index and explicitly demonstrated its equivalence to Cohen's D from a between subject randomized experiment. They proposed methods for estimating the effect sizes from data collected in treatment reversal designs in 2012 and multiple baseline designs in 2013. For both designs, the effect size estimators were designed to be expressible using closed form algebra. Therefore, that approach relied on several restrictive assumptions, including that baselines are stable, lacking any trends, that the intervention effect can be modeled as a shift in the mean level of the outcome, and that the treatment effect is homogeneous across cases. This limited the applicability of the effect size. Therefore, in 2014, Pustiowski and colleagues further developed this framework and developed effect sizes on a variety of more flexible models. This effect size estimation approach involves modeling the data from treatment reversal and multiple baseline, multiple probe designs with a hierarchical linear model that accommodates the nested structure of single case design data. Crucially, the hierarchical model captures variation in the outcome both within and across participants, making it possible to estimate a standardized mean difference effect size that is comparable to what would be obtained from a between group design. However, because the design comparable effect size index involves a cross-participant variation in the outcome, it is only possible to apply the approach in designs that include multiple individuals, at least 3. Consequently, the methods are not available for single case experimental designs based on just a single individual. In practice, the most basic version of the design comparable effect size estimation methods require that the study includes at least 3 individual cases. Studies with more cases are ideal for increasing the precision of the effect size estimates and for calculating effect sizes based on more complex models. As mentioned on previous slide, the original HSP estimator was expressed using closed form algebra, using moment estimation techniques, and relied on several restrictive assumptions. Thus in 2014, Pustiowski and colleagues presented a more flexible modeling approach, and the effect size estimation procedure is based on a small sample correction to the restricted maximum likelihoods. So this more flexible estimator is also more readily extensible than the previous HPS estimator. Now the 2-level modeling framework to estimate the design comparable effect size will be introduced on next slide. Some of you might already be familiar with the two-level model that can be applied to estimate the design comparable effect size. However, for others, this might be completely new. Therefore, to bring all of you at the same level, I'm going to go over some details needed to understand the hierarchical linear modeling framework that is used to estimate the design comparable effect sizes. So I'm going now to provide a general basic introduction to the logic behind the design comparable effect size for the most basic model, also called the original model. Suppose that the single case design study includes a total of I cases, and I is equal then or larger than 3. And that case I is measured for a total of M measurement occasions. Y underscore IT indicates the outcome for measurement occasion T for case I. And intervention underscore IT is an indicator variable equal to 1 if case I was in the intervention condition during occasion T, and equals to 0 if case I was in the control condition during occasion T. The individual level model for the outcome measurements of case I is then displayed in the following level 1 equation. So YIT equals beta 0I plus beta 1I times the intervention indicator plus E underscore IT. Beta 1I indicates the expected intervention effect, so change in the level of outcome upon introduction of the intervention for individual I. And beta 0I is then the expected baseline outcome level for individual I, that is when the indicator variable intervention equals 0. The errors indicated by E are assumed to be normally distributed with mean 0 and variance sigma squared. And the errors for case I follow a first order autocorrelation. Now, to complete the model, we must then make assumptions about how the individual level coefficients beta 0 and beta 1 vary across cases. Specifically, the original model assumes that individual specific intervention effects are equal across cases, so that theta 1 represents the common change in level of the outcome upon introduction of the intervention. With other words, the beta 1s are fixed across cases. They are not allowed to vary. In contrast, the original model assumes that the baseline levels, the beta 0s, vary across cases. For instance, some individuals might have higher baseline levels compared to other individuals. Therefore, the beta 0s equal an overall across case baseline level and a deviation U. This deviation reflects the degree to which individual I deviates from the overall baseline level theta 0. These deviations are assumed to be normally distributed with mean 0 and variance tau squared. This is reflected in the level 2 equations. So beta 0I equals theta 0 plus ui, and beta 1I equals theta 1. Now, theta 1 indicates the expected unstandardized intervention effect across the I cases. Note also that the within case variance, sigma squared, and the first order autocorrelation are assumed constant across cases. Under the assumptions of this hierarchical model, the design comparable effect size parameter, indicated by delta in the equation on the right-hand side, is defined as the unstandardized intervention effect across cases, so theta 1, divided by the root square of the within case variance, sigma squared, and the between case variance, tau squared. With other words, the numerator reflects the unstandardized intervention effect across cases, and the denominator represents the standard deviation of the outcome, so including both within and between case variation. The basic hierarchical model introduced on previous slide can be extended in two main ways. First, by using a more flexible individual level model, and second, by making different assumptions about how the individual level coefficients vary across cases. An example of this extension is provided on the next slide. So we might assume that the outcomes for case I follow a linear trend during the control condition, and that the introduction of the intervention leads to an initial change in level as well as a change in the slope of the time trends. In order to account for these time trends, the level 1 equation can be extended as displayed on this slide. Using a more flexible individual level model requires making further assumptions about how the coefficients of such a model vary across cases within the single case design study. The original formulation of the model assumed that only the baseline levels of the outcome varied across cases, while constraining the intervention effect to be constant across cases. This restrictive assumption is not necessary with this more general formulation. One could instead allow the intervention effect to vary across cases as well. And if the individual level model includes time trends for the control or intervention condition, then one must also make assumptions about how the time trends vary across cases. So in principle, we could allow all of the time trends to vary across cases as well. However, given the small number of cases available in most single case design studies, making more parsimonious assumptions will be necessary in practice. Now, in defining effect sizes under more general models, using these more flexible models introduces additional complexities into the definition of the design comparable effect size. Recall that the design comparable effect size parameter has two components: numerator that represents the unstandardized intervention effect across cases, and a denominator representing the square root of the total variance in the outcome, so including both within and between individual variation. However, in models that include time trends during the intervention condition, the unstandardized intervention effect is not constant anymore across time points. Similarly, in models in which the time trends in either phase vary across cases, the total variation in the outcome is also not constant anymore across time points. The design comparable effect size, as introduced on previous slides, is approximately unbiased if the number of cases is large. However, for sample sizes typically found in single case design studies, the design comparable effect size may be biased. Now, this bias can be corrected by using methods described by Hedges, similar to what has been done to correct the small sample bias of the Cohen's D statistic from a between subjects experiment. The corrected effect size estimate is often referred to as Hedges G. So it is advised to implement this small sample size correction to the design comparable effect size. The bias corrected effect size estimator is displayed on the slide. G refers to the bias corrected design comparable effect size and equals the estimated delta, so the design comparable effect size estimate, multiplied by a correction factor. Now, the correction factor is a function of the degrees of freedom V. The larger the number of cases, the larger the V. The V is in the denominator. Therefore, the larger V, the smaller the part that is subtracted by 1, and so the smaller the correction needed. The SCD HLM Shiny tool that the second presenter, Danny, will introduce in a little will provide the design comparable effect size corrected for this small bias. And with that, I will turn the webinar over to Danny, who will discuss appropriate use of the design comparable effect size and provide an application.
Hi, everyone. First, I want to thank Mariola for that really excellent introduction to the design comparable effect size. As she mentioned, I'm first going to briefly touch on the appropriate use of the D-CES. Mariola already discussed many of the requirements for estimating the D-CES, but I want to talk about a few important applied considerations when you're trying to apply the D-CES on your own. Once I've done that, I'm going to walk through a demo of using the SCD HLM Shiny app. The first important consideration I want to emphasize is that the design for which you estimate a design comparable effect size has to allow for comparisons across participants. So that might be a multiple baseline design across participants, or a treatment reversal design that has 3 or more cases measured on the same outcome. So for an example of a case where it wouldn't be inappropriate, and we actually just had a question about this, so I'm glad somebody asked this, but if you imagine a case where a researcher is evaluating a behavioral intervention for a single student with a behavioral disorder, the researcher might use a multiple baseline design to evaluate the effects of the intervention in a full classroom context, in a pull-out context with an interventionist, and in a home learning context. While this multiple baseline design across contexts has 3 tiers, it doesn't have 3 actual cases. You could estimate that hierarchical model that Mariola described with this data, but the resulting model components wouldn't be exactly the same. You would be estimating a within context variance and a between context variance, not a within case and between case variance. So if you estimated the effect size from those model components, the resulting effect size would not be truly comparable to an estimate that came from a group design. The other important study design consideration is that outcomes used to estimate a single design comparable effect size estimate should all be the same measure. So for instance, I've seen SCD studies of interventions for social behaviors where you've got 3 participants, and maybe Jose and Yolanda's primary outcomes are positive social behaviors, and in contrast, Anna's is negative outbursts. This wouldn't be an appropriate study for estimating the D-CES. Later, if you add some studies of an intervention for social behaviors which primarily focused on positive behaviors, and then a set of different studies which primarily focused on negative behaviors, you could eventually use meta-analysis to synthesize an overall effect for that intervention. And finally, Mariola noted that you can expand the formulation of the multi-level model used to estimate the design comparable effect size for time trends or for treatment heterogeneity. I would be very cautious when expanding the model beyond the basic differences in mean specification. As Mariola noted, there are very complicated considerations about when you estimate an effect size for, if you have differing trends, and it has a sort of meaningful impact on the definition of the effect size. This doesn't mean that you should never use the more complex modeling specifications that are available, but you should really ensure that you understand the potential consequences of any additional assumptions that you're making before you proceed. That wraps it up for the appropriate use section of the webinar. In a moment, I'm going to demo the SCD HLM Shiny app. Before I do, I just want to note this app is produced by Dr. James E. Pustiavsky for estimating the design comparable effect size. James Pustiavsky also calls this the between case standardized mean difference, or the BCSMD. They are exactly the same thing. There's no difference, so don't be confused by the differing terminology. Although the WWC does not endorse any particular software for estimating an effect size, at the present time, the SCD HLM package in R is the only prepackaged method for estimating the D-CES using restricted maximum likelihood, or REML, as opposed to the moment estimator. For those of you who don't know, Shiny apps are a way of putting a nice user interface on functions from an R package, so you don't have to spend time messing around with the command line if you're not comfortable with R or writing your own R code. James hosts the app on the Shiny Apps website. It's also possible to run the app on your computer locally without connecting to the internet. This can be useful if the app is down for some reason, or if you want to estimate the effect size with sensitive data that you cannot upload to the internet. Finally, if you're comfortable writing your own R code, you can accomplish everything the app can do and a little bit more by using the command line interface and writing your own code. At this time, I'm going to take control of the webinar and show you my screen. So give us just a second while we switch views. Okay. So before we look directly at the app, I want to make a note about how the SCD HLM app expects your data to be organized. The app expects your data to be organized in a long format. If you're organizing your data in an Excel spreadsheet like this one, each row of the sheet should be a single observation with enough information to identify an individual case, the phase, and the session number associated with each observation or outcome data point. I've organized my data in approximately the format that the app expects. It's actually exactly the format the app expects. This is example data from Dunlap, White, Vera, Wilson, and Panachek, published in 1996. I extracted the data from the study plots myself. The WWC has previously reviewed the study under the 3.0 pilot standards, and the study received a rating of meets WWC standards with reservations. All right, and let's switch to the app now. If you follow the link in the chat box to the SCD HLM app, you should see something that looks like this. As a side note, if a lot of you are trying to access the app right this second, it might be very slow or it might not load at all. Usually it's no trouble to use the app online, but this is one of those cases where it might be tough because there are 100 or more of you trying to look at the app right now. I am actually going to present the app locally on my own computer. As I said, it's great for when it's tough to access the app for some reason. And this way I'll avoid any difficulties with the online version. They should look identical. On the first tab of the SCD HLM app, called SCD HLM, there's information about the authors and contributors to the app, the suggested citation if you use the app in your own research, and a tutorial paper about the app and the D-CES in general. If you click down the options on the menu on the left side, so let's click right here, you can also see that there are directions for accessing the app, including directions on how to access the app locally in RStudio. There are further methodological references if you're interested in understanding the nuts and bolts of the D-CES. The app also has a number of example data sets built in for individuals interested in playing with the app, but who do not want to or don't yet have their own data to use in the app. And this final section provides references to the primary studies that this data was drawn from. If we move on to the Load tab, we can start using the app. You can see that there are 3 options for using the app. First, you can use one of the example data sets, and you can see that there are about a dozen examples that you can choose between. You can upload a CSV or a text file containing your data, so long as it's been formatted properly. Finally, you can upload an XLSX file, which is the most recent version of the default Excel format. I'm going to upload an XLSX in the form of the WWC Study Review Guide for SCDs with just the data tab filled in. This is the document that reviewers use to review single case design studies. I'm going to click on the Browse button and then browse to the file that has the data that I'm going to estimate the effect size for. I click Open. I'm going to leave the file as header box checked. You only want to uncheck that if your file doesn't have names for all the columns, but as we saw before, my file does have column names. Finally, I'm going to select the sheet where the data is contained, and in this case, it is helpfully named data. As I uploaded my data, you would have seen some options for specifying important details appear here on the right. Going down the list, you first need to specify the design type. You can see there are 2 options, treatment reversal or multiple baseline / multiple probe. This is a treatment reversal design, so I'm going to leave treatment reversal checked. Next, I'm going to select the variables that have each type of information. First, I'm going to select participant name or ID, which corresponds to my case identifier. Then I'm going to select my phase identifier, which is helpfully phase name, and it's already selected. I'm going to select my session number, which is the x-axis, already set a session number. I'm going to select my outcome value, which is the y-axis, and again, it's already been selected. Then you need to specify the baseline and treatment levels, the values inside your phase identifier that correspond to your baseline and treatment or intervention level. Every case in your data set should use a common identifier for all of the baseline phases and a common identifier for all of the treatment or intervention phases. If you have a reversal design like this one, and you give your first baseline phase an identifier like A1, and then call the second baseline phase or the return to baseline phase something different like A2, the app won't understand that and it won't know how to estimate the effect size. So you see here, I've just got a baseline and intervention labels. And I've selected baseline for the baseline level and intervention for the treatment level. Finally, you can also filter on variables. If you have, say you have more than one outcome and you want to estimate an effect size for one outcome and then turn around and estimate an effect size for the next outcome, you can select the variable that corresponds to that outcome type. I only have one outcome, task engagement, in my data set, so I don't actually have to filter, but I just wanted to show you what it looks like. If you move on to the Inspect tab, you can see how the app understands the way you've organized your data. Take a moment to look at the data in the SCD HLM graph tab and the original plots from the studies that you're estimating an effect size for. They should generally look reasonably similar. The only reason they might not look similar is if the scale of the plots aren't the same. For instance, if the minimum or the maximum, the Y or the X axis are different than they are in the original study, the plots are going to look a little bit different. So you'll have to inspect the data to make sure that everything looks good. You can also see that on the right side, there's just there's just baseline and intervention. There aren't more than two levels of the outcome or of the intervention. You can also look at the data tab to see the way that you can see the data the app is going to use to estimate the effect size. The variables that's just selected as your case, session number, phase identifier, and the outcome variable will be the first four columns. The second two columns are values the app will use internally to estimate the multi-level model for the D-CES, so you don't need to worry about those too much. You can also take a moment here to make sure the values in this data tab are the values that you expect. If we move on to the model tab, this is where you can specify more complex models. At the moment, the default specifications, the default selections in the SCD HLM correspond to the default model specification that the WWC uses. However, that might not always be the case. So if your reviewer is going to estimate the effect size, it's important to have a general understanding of what's going on here. The first dropdown lets you choose between the moment estimator and the restricted maximum likelihood or REML estimator that I referred to earlier. The WWC uses the REML estimator. Then we estimate a fixed effect of the level and a random effect for the baseline phase. These are already selected, as you can see. For the treatment phase, we only estimate the fixed effect for the level, and we do not estimate a random effect for the level. For a treatment reversal design, the app doesn't allow for more complex modeling specifications because doing a more complex model in a treatment reversal design is pretty tricky. I'll come back to this briefly in a second and show you what this looks like when you have a multiple baseline design. You can also see a graph of the model estimates at the bottom. And if you click on the model estimates tab, you can see some of the code the app uses to get at the D-CES. But you don't actually need to look at this usually. And there's a new feature I'll talk about in a minute that's going to be really helpful if you want to see the code the app is using to estimate the effect size. If you click on the effect size tab, you can see information about the effect size. The WWC's study review guide asks you that you collect the effect size, the standard error, and the autocorrelation. But no matter what kind of review you do, you're going to want the effect size estimate and the standard error. Although just about anything on this page, and it's quite a lot of information, could be of interest. Finally, I want to show you, and at this point, you want to go ahead and document this information in your study review guide if you're a WWC reviewer, or in whatever document you're using to track effect sizes if you're doing your own review. So over the weekend, James Pustiowski updated the app. Nothing important has changed in terms of estimating the model, but there is an additional tab called syntax for R. What this does is provide R code or syntax that you can use to replicate what the app has done to get the effect size and the plots. So if you want to make sure that your effect size estimation is replicable, you could copy and paste this code and use it on your own data to get at what the app has done. Finally, I want to show you what the app looks like when you're doing a multiple baseline design. So I've returned to this load tab, and I'm going to use one of the examples, this Abler-Morgan example, which is a multiple baseline design. You can see all those options on the right side disappear when I selected the Abler-Morgan example, because this has all been pre-specified. We can look at the Inspect tab to see what the data looks like. It's kind of an upside down multiple baseline design. The ordering of the tiers doesn't matter for the app. So although it's not kind of in the order you might expect, if you're a single case design researcher, it's not going to affect the design comparable effect size. We can see how the data is organized like we did before. We can go to the model tab. And now you can see there are some options, some additional options. There's this center session at on the right near the top. You can include more complex modeling specifications, limited by the amount of data that you have. And on the effect size page, you can choose these sliders, which set the initial treatment time and the follow-up time. When you're using the basic specification that doesn't include the more complex linear trends in the linear or nonlinear trends in the baseline or intervention phase, and that assumes a homogeneous effect size, these don't matter. This only matters if you're doing the more complicated modeling that is available for the D-CES. And that's a topic that's a little more complex than we have the time to get into today. But I just wanted to show you what it looked like when you were using those options, and just to say that these sliders are not important when you're estimating the basic differences in means, and so you can leave them alone. This ends the live demo portion of the training, and we will return to the slides. So before we move on to the Q&A, I just want to mention that the WWC SWAT team has recently produced a flowchart or infographic to help reviewers and review teams move through the process of estimating an effect size from a study they have determined should be included in a review. This may be a little tough to read, and we're not expecting you to read it right now. This will be available soon on the WWC resources page, and we'll let you know when it becomes available. This is the top half of the flowchart. It moves through some of the important decision points for a WWC review, including when to extract data from graphs in a primary study. Even if you're not performing a WWC review, this flowchart might be helpful for this part of your own reviews. This second half talks through the process of reconciling reviews. The WWC double codes all of the studies it reviews in some fashion. If you're performing a review on your own, as opposed to a WWC review, it's advisable to double code at least some, if not all, of the studies you are reviewing. This section of the flowchart can help you think about reconciling the double coding to ensure that the effect size estimation is reliable. All right, thanks for your time, everyone. At this time, I'm going to turn it back over to Emily for our Q&A.
Fantastic. Well, thank you so much, Mariola and Danny, for helping us understand this design comparable effect size and its value and utility for quantifying intervention effects in single case design research. So now for this last 11 minutes that we have together, we'd like to take some time to address some of the questions that we've received from participants in the chat box. And again, just a reminder to folks that we may not have time to address all of the questions we've received today. However, we will be responding to all questions received and including those responses in the archived webinar materials. So the first question that we've received here, Mariola, I'm hoping you might be able to address this. So the question is, is the design comparable effect size intended for computing a between subject effect size or a within subject effect size?
Thank you for the question. So let me first start with clarifying the difference between a between subject effect size for single case designs and a between subject effect size for the between subject designs. So the design comparable effect size, as I explained during the first part, is used to reflect intervention effectiveness across subject. So that is reflecting the effect size at the study level. So for that, the within case and between case standard deviations are used to standardize the coefficient. And so this is different from an effect size that is used from between subject designs, such as the HSG, because HSG only uses the standard deviations of scores from cases, and that in the control condition or a pooled standard deviation or the standard deviation of the intervention condition. So the between subject design does not have that within subject standard deviation because there are no repeated measures within control and intervention conditions. So therefore, usually the standard deviation of the control condition, for instance, is used to standardize. So to sum it up, yes, this design comparable effect size, it is a between subject effect size for single case studies, but that at least with 3 participants. And then others, effect sizes such as coherence D, HSG, they are the between subject effect sizes for between subject designs. So I hope that clarifies and gives an answer to the question.
Great, thank you, Mariola. So Danny, I'm hoping you can address this next question, which we received, which is how should reviewers handle reviews and reconciliations when the 2 different reviewers obtain different values using that design comparable effect size calculator?
It's a great question. The flowchart that I presented just a moment ago walks through this process, but since it's not available yet, I'm going to briefly recap that part of it here. There are 2 places in this process that might result in reviewers reaching somewhat different values or very different values in the D-CES. The first place that reviewers might get different values is if the reviewers are extracting data from a plot. When extracting outcome data from plots presented in a single case design study, there will likely be some measurement error in the extraction process, and this is expected. So as a consequence, we don't anticipate that extracted outcomes or the resulting effect sizes will be exactly the same across the 2 reviewers. Therefore, the best approach will be to estimate a reliability coefficient of the individual outcomes between the 2 reviewers, ignoring the final D-CES estimate to begin with. For specific guidance about reliability, the WWC Standards and Procedures Handbooks already have some guidance about reasonable measures and minimum benchmarks for acceptable levels of reliability. So if the 2 reviewers' extracted outcomes are not reliable with each other, I would first look for obvious mistakes with one of the reviewers' extracted data. This might look like values that are out of range of the metric. So counts that are well below 0, or percentages or proportions that are well below 0 or well above the 100% mark would indicate that there was some error in the extraction process. Assuming that there are no obvious errors that are identified, you should probably request that your reviewers re-extract the data from the plots a second time and just ask them to be a little more careful to ensure that they correctly follow the process of setting the scale of the plots and extracting the individual data points. If the outcomes themselves meet the threshold for reliability, then we're not worried about differences between the 2 effect sizes. So our next recommendation, if the outcomes meet the threshold for reliability, just make sure that they have used the same modeling specification for the multi-level model used to estimate the design comparable effect size. If those 2 modeling specifications match and the reliability estimate is acceptable, then either reviewer's design comparable effect size estimate will also be acceptable for the purposes of the synthesis. At this point, you can either choose one of the estimates or at random, so flip a coin maybe, or average the 2 together. So that modeling specification step is the second place in the process where the 2 reviewers might end up with different values. If the reviewers are using raw tabular data, either from the primary study or as a result of a request to the author for their data, the effect size estimates should be exactly the same if the reviewers are using the same modeling specification. So if they're using that raw data and they have different effect sizes, then you want to make sure that they've got the same modeling specification. If they do have the same modeling specification and they have the exact same effect size, at this point, obviously, you don't need to average or pick at random because they should be the same. Reviewers should be careful to document any deviations from the default modeling specifications that are described in the Procedures Handbook, and only do so with careful consultation with the leadership of the review. I hope that answers that question for anybody out there.
Great, thank you, Danny. So we've got another question here, Danny, that I'm hoping you can address. And so this is shifting gears a bit, but how much confidence do we need to have in the functional relationship between the independent and dependent variables based on visual analysis to justify calculating an effect size?
So this is a really great question. And for the purposes of this question, I'm going to assume that you're talking about the confidence needed to calculate an effect size to be included in a synthesis or review, although this will probably still be relevant for individual studies. So the WWC Standards and Procedures Handbooks version 4.1 do not require a formal visual analysis before the estimation of effect size. There is potentially some value to conducting visual analysis alongside the estimation of an effect size, and we'll address that shortly in response to another question. But relevant to the question at hand, we would suggest estimating an effect size whether or not your visual analysis provides evidence of intervention effectiveness, if the design supports it and you do not think that there are serious internal validity flaws in the study. So if no effect is present, but you think that's really no effect, you'd still want to estimate the effect size. The WWC considers internal validity via the single case design standards, which are primarily concerned with the number of cases and/or phases in the design, with the number of observations in each phase, and some other design-specific requirements. The reason the WWC estimates an effect size for all studies that meet design standards is because of the meta-analytic approach the WWC uses to synthesizing research effects on the effectiveness of an intervention. This process works in 3 stages. First, we ask, do we trust whatever the results of the study are based on the design and potentially some of the features of the implementation? Again, this is reflected in the WWC's design standards. If and only if the answer to the first question is yes, we ask the second question, which is, what is the magnitude of the intervention effect and how much uncertainty is there around that effect? Finally, when we perform a synthesis, we ask, what is the average effect of the intervention and how much uncertainty is there around that average effect? That last step requires that we include null effects or even negative effects reported in the literature, even if the overall distribution of effect size indicates that the intervention generally has a positive effect. Leaving those estimates of small or even negative effects out of the synthesis will result in overstating the average effect size or the average effect of an intervention and may yield the incorrect conclusion that an intervention is more effective than it truly is. If we require a functional relationship in order to include the effect in the synthesis, we would systematically exclude those negative or null effects, which would lead to a biased conclusion about the intervention's average effectiveness.
Great, thank you for that clarification, Danny. So Mariola, I think we've got time for one more question I'm hoping you can answer, which is, if the functional relationship is questionable, can we still calculate the design comparable effect size by making baseline adjustments? And if we proceed down that path, what limitations would our research findings have?
Yeah, thank you so much for this great question. So it's important to recognize first that not all issues with functional relations are trends. Some are simply issues with variability that are difficult to control for statistically. So as discussed during the webinar, if you do have an issue of therapeutic trend, you could potentially include baseline trends in the multi-level model used for effect size calculation. However, the simplest version of this will simply estimate an average trend across all of the cases you have included in the model to estimate your design comparable effect size. So if you only have one case with a problematic therapeutic trend, the estimation model will average across all of the baselines for all of the cases in the study. And that, of course, will impact the effect of the treatment in aggregate. So not just for the cases with the problematic slopes in the baseline. And so if there is slope heterogeneity, you could also potentially estimate random slopes. However, you will need more cases than a minimum of 3 to do this with much success. And it also has consequences for the effect size calculation, as I mentioned during the webinar. So and the more complex, of course, the model specification, the larger standard errors will be. And so this will have consequences for research synthesis, and it will definitely have consequences too for statistical significance. And then finally, if you include any sort of controlling for baseline trend, you want to do it in every case for your synthesis. So including those studies which do not appear to have a trend or have contra-therapeutic trends that visual analysis might not find troubling are considered worth controlling for.
Great. Well, thank you so much, Mariola. So with that, we're right at time here. And so this concludes our webinar for today. I would like to thank our presenters again, Mariola and Danny, for such an engaging and informative webinar. And just a reminder to folks that the WWC Statistics website and training team engages in webinars throughout the year to highlight important aspects of the WWC. Our planned webinars vary in topics, but they all share the goal of increasing familiarity and knowledge of the WWC standards and procedures. To learn more about webinars offered by the WWC and IES, be sure to sign up to receive those notices through the IES listserv. And you can follow the link in the chat box to sign up for that listserv if you're not on it already. And again, just a reminder to everyone that we'll be posting an archive of today's webinar, so the slides, the recording, along with responses to all questions received, including those we did not have time to cover today. So if you do have any additional questions for the presenters, please feel free to email those to the WWC's help desk in the chat box with that link. And with that, I thank you again for joining us today, and we hope you'll join us again soon.